Welcome back to linear algebra. In this video, we're going to be analyzing the properties of eigenvectors. Last time, we saw that the eigenvalue problem, ax equals lambda x, has specific values of lambda where there are solutions, and for most values of lambda, there is no solution. In this video, we're going to be taking those eigenvalues and looking at how to describe the corresponding eigenvectors. The first thing I want you to notice is that there are infinitely many eigenvectors for any given eigenvalue. If I take an eigenvector and multiply it times k, I can take that k out front, and then I have a times x, and because x is an eigenvector, the corresponding eigenvalue shows up. And then using the commutative and associative properties of scalar multiplication, if you have an eigenvector x, then any scalar multiple of that eigenvector is also an eigenvector. And in fact, any linear combination of eigenvectors is also an eigenvector. So eigenvectors are going to form a vector space. With these ideas in mind, let me get my head out of the way so we can start really talking about this. And after making such a big deal about the fact that the zero vector is never an eigenvector, in order to have a vector space, we do need to have that zero vector back in. So the zero vector is in the eigenspace, even though it is not an eigenvector. And every other eigenvector is in the space, and nothing that is not an eigenvector is in the eigenspace. And for an n by n matrix A and a particular eigenvalue lambda, the eigenspace will form a vector subspace. And that's another one that I would like you to try to prove on your own. Instead, I want to start looking at a couple of specific examples. Let's start off with a matrix that we have already encountered. Matrix A is 3, 0, 8, negative 1. We saw last time that there are two eigenvalues for this matrix, lambda equals 3 and lambda equals negative 1. So if I want to find the eigenvectors corresponding to each eigenvalue, since there are infinitely many of them, I'm going to really be looking for the eigenspace, the set of all vectors. If I can find a basis for it, so much the better. So when lambda is equal to 3, we have that ax is equal to 3x. And as we've seen before, we can rearrange this and write it as a minus 3I times x is equal to the 0 vector. And a minus 3I is 3 minus 3, 0, 8, negative 1 minus 3. Of course, 3 minus 3 is 0. And without having to do too much work on this, components of vector x will be scalar x, scalar y. We get the equation 8x minus 4y is equal to 0. And we get that y is equal to 2x. So in general, x is going to have components x and 2x, or 1, 2 times scalar x. So any scalar multiple of the vector 1, 2 is an eigenvector for this matrix corresponding to eigenvalue lambda equals 3, and the eigenspace is the span of vector 1, 2. I invite you to do the same thing for I invite you to do the same thing for lambda equals negative 1. For the sake of time, I'm not going to go through it. You can pause the video and try to work through it before I give the solution. But you get that the eigenvectors corresponding to lambda equals negative 1 are vectors in the form 1, 0, or scalar multiples of 1, 0. So the vector space, the eigenspace, is the span of vector 1, 0. Let's take a look at another example here. This time, let's take a look at a matrix we haven't analyzed before. And we want to find the eigenvalues and corresponding eigenvectors for matrix A, which is given as 0, 0, negative 2, 1, 2, 1, 1, 0, 3. And we can find the eigenvalues by setting up the characteristic equation. I'm going to jump through the algebra, a minus lambda I, etc. And after doing all that, we want the determinant of negative lambda, 0, negative 2, 1, 2 minus lambda, 1, 1, 0, 3 minus lambda. And it looks like expanding across the first row won't be too bad. But if we expand across the second column instead, we'll get a really easy result. All right, so that's going to be index of 3, 4, and 5. So it'll be negative, positive, negative instead of the positive, negative, positive pattern we usually get. But you'll get 0 times the determinant of the 2 by 2 matrix by removing the first row and second column, plus 2 minus lambda times the determinant of the 2 by 2 matrix you get by removing the second row and second column, negative lambda, negative 2, 1, 3 minus lambda, and then minus 0 times the determinant of the matrix you get when you eliminate the third row, second column. And I don't really care what those are because the determinant of any matrix times 0 is still 0. All right, expanding out, we get negative lambda times 3 minus lambda minus negative 2. And we can multiply this out. In fact, I'm going to leave that 2 minus lambda in front. That looks like that's going to be very convenient for us. Two minus lambda times lambda squared minus 3 lambda plus 2. This is the characteristic equation. We set that equal to 0. The 0 product rule tells us that either 2 minus lambda is equal to 0, or lambda squared minus 3 lambda plus 2 is equal to 0. And lambda squared minus 3 lambda plus 2, you could use the quadratic formula if you would like, but this factors pretty nicely. It's going to be lambda minus 2 times lambda minus 1. Right? And here is an instance of multiplicity. Lambda equals 2 is a repeated root for this particular characteristic polynomial. And the repeated roots tend to be where some strange things can happen. They don't always, but those tend to be the more interesting ones. I encourage you to look for the eigenspace for the eigenvalue lambda equals 1 on your own. I'm going to spend some time looking at the eigenspace for the eigenvalue lambda equals 2. So for lambda equals 2, we're looking at the equation ax equals 2x, or a minus 2i x equals 0 vector is a much easier way of dealing with that. And when we perform that a minus 2i, we get the 3 by 3 matrix negative 2, 0, negative 2, 1, 0, 1, 1, 0, 1. And once again, you could use matrix methods, but this particular matrix was chosen so that the characteristic equation or the solutions here are fairly straightforward to find. Taking the components of eigenvector x to be scalar x, scalar y, and scalar z, you get negative 2x minus 2z equals 0, which has solution x equals z, and you have, I'm sorry, x equals minus z. I wrote that and I didn't say it right. Then you have x plus z equals 0, which also has solution x equals minus z. And you have the third row also gives you x plus z equals 0, same solution. All right, so if we take our vector x, y, z, we can set component x to be anything we'd like. We can set component y to be anything we'd like. The only thing that we're forced on is that if x is equal to s, then z has to be equal to the opposite of s. So our solutions here are a linear combination of two vectors. Notice, because the zeros are in different places, that these two vectors are linearly independent. So they can form a basis for the solutions. And the eigenspace for this matrix corresponding to the eigenvalue lambda equals 2 is the span of the vectors 1, 0, negative 1 and 0, 1, 0. Using any one of the myriad of different ways of denoting that. Setting this up slightly differently would give you a slightly different basis vectors that are equivalent, so it all works out. Here's an interesting result on how eigenvalues and eigenvectors relate in combination. Let A be any n by n matrix with and pick some distinct eigenvalues, lambda 1, lambda 2, up through lambda k. So remember, matrix A can have at most n distinct eigenvalues, but as we saw in the last example, it doesn't always have that many. And every eigenvalue has infinitely many corresponding eigenvectors. We are picking one eigenvector to come from each eigenvalue. We have distinct eigenvalues. We are taking one of the eigenvectors for each eigenvalue. And no matter how we choose that, that set of eigenvectors is linearly independent. The proof of this theorem is a little bit esoteric, but it involves one of my favorite techniques, so I'd like to go through it. The statement of this theorem doesn't quite give us enough information to really push forward with the whole idea of linear independence. So we need to make another assumption somewhere. The way we're going to do that is to proceed by contradiction. I'm going to assume that this theorem is false. That is to say, I'm going to assume that the set x1, x2 through to xk is linearly dependent. And I'm going to hope that by the end of this, I get complete garbage. Because if I get complete garbage, that means I made a faulty assumption. And my only assumption is that this set is linearly dependent. If it is falsy, that means that it's not linearly dependent, and that's the definition of linearly independent. All right. The way that this proof is going to work is that there must be a boundary where we go from linearly independent to linearly dependent, if it is the case that these vectors are linearly dependent. Because if we had just one vector, we would have a linearly independent set, unless that vector was the zero vector. But we know that x1 is not the zero vector, because x1 is the eigenvalue corresponding to, or the eigenvector corresponding to eigenvalue lambda 1, and eigenvectors are never the zero vector. The zero vector is not an eigenvector, even though it satisfies the eigenvalue problem, because that just makes eigenvalues actually useful. So we have a linearly independent subset of a linearly dependent set. So because we know, again, it's our false assumption, but we're assuming that x1 through to xk is linearly dependent. x1 by itself is linearly independent. So there has to be an r somewhere. It could be 1 itself. It could be all the way up to k minus 1, but it won't be k. So that when you take x1 through to xr, you get a linearly independent set. And when you put one more vector in, it turns into a linearly dependent set. Again, we're proceeding by contradiction. So we're going to show that this is nonsensical to assume that this is going to happen. And that's exactly what we want. The definition of linear dependence is that if I take some constants, C1, C2, up through to CR plus 1, not all 0, I should be able to find a linear combination that gives me the 0 vector. Right? The fact that we have linearly dependent vectors tells me that this must happen. There must be some values of C where they are not all 0, and yet this still occurs. And then from here, we get kind of goofy, because we don't know a lot about the vectors x. The only thing we know is that they are eigenvalues. So this equation is going to be useful. I'm going to call it dagger so I can refer you back here again. But let's go ahead and apply the matrix transformation A to equation dagger on both sides. That gives me that A times C1 x1 through to CR plus 1 x R plus 1 is equal to A times the 0 vector. On the right-hand side, anything times the 0 vector is equal to the 0 vector. On the left-hand side, we can distribute so we get A times C1 x1, A times C2 x2, A times C3 x3, till we get to A C R plus 1 x R plus 1. And then multiplying matrices and scalars, we can put the scalar anywhere we would like and everything still works out. So I can pull the scalars out in front. On each one of those terms. And I said that the reason that I wanted to do this was that the vectors x are all eigenvectors of the matrix, which means that if I multiply A times the eigenvector, I will get the eigenvalue times the eigenvector. So this is C1 times lambda 1x, C2 times lambda 2x, all the way to CR plus 1 times lambda R plus 1 times x R plus 1. All right, that's also going to be a useful equation for us in a little bit. So I'm going to go ahead and name that as double dagger. Now, before equation dagger gets off the screen, I want to do something else with it. I'm going to instead multiply equation dagger by lambda R plus 1. So I will get lambda r plus 1. Let's try that again, actually fitting everything in. I will get on the left-hand side lambda r plus 1 times c1 x1 through to c r plus 1 x r plus 1. And on the right-hand side, I get lambda r plus 1 times the 0 vector. Let's keep equation double dagger on the screen if we can. Distributing over here, I've got c1 lambda r plus 1 x1 and c r plus 1 lambda r plus 1 x r plus 1 at the end. On the right-hand side, anything times the 0 vector is the 0 vector. So that gives us something nice to work with. Then from here, I am going to subtract equation double dagger from this equation. And I'll do that term by term. So I've got c1 lambda r plus 1 x1 minus c1 lambda 1 x1. I've got c2 lambda r plus 1 x2 minus c2 lambda 2 x2, all the way to the end where I will have c r plus 1 lambda r plus 1 x r plus 1 minus c r plus 1 lambda r plus 1 x r plus 1. And on the right-hand side, I have the 0 vector minus the 0 vector, which is the 0 vector. At this point, I have to start introducing some more of the intermediate terms. So notice here I can factor. The c is the same, the x is the same, so I'm really just subtracting the stuff in the middle. I have c1 lambda r plus 1 minus lambda 1 times x1. I have c2 lambda r plus 1 minus lambda 2 times x2. I will have CR lambda r plus 1 minus lambda r XR, and I will have CR plus 1 lambda r plus 1 minus lambda r plus 1 XR plus 1. When I add all those together, sorry about that, I accidentally hit my scroll bar. When I add all those together, I get the 0 vector. The important thing in all of that, right here in the last term, I have lambda r plus 1 minus lambda r plus 1, which is 0. That goes away. And I really just have the rest of all of this equals the 0 vector. And as hideous as that algebra is, that's the whole story. Notice that I now am looking at the set x1 through to xr, which we said was linearly independent. And A linearly independent set of vectors means that if you take a linear combination, which is what we're doing here, and get the zero vector, that means that C1 times lambda r plus 1 minus lambda 1 is equal to 0, and C2 times lambda r plus 1 minus lambda 2 is equal to 0, and etc. But all of the eigenvalues, lambda i's, are distinct. And lambda I being distinct means that lambda r plus 1 minus lambda I is not 0. And the CI's are not all 0. So at least some of the coefficients here are non-zero. This is a contradiction. The only thing we assumed was that the set of eigenvectors was linearly dependent. We arrived just from that, after a lot of ugly algebra, at complete nonsense. That means that our assumption must be false. It is false that that set of vectors is linearly dependent, and the only thing that leaves is that that set of vectors is linearly independent. All right. With that, I am going to wrap up our discussion here, given a little bit of an idea of how to find eigenvectors and some of the geometric reasons that eigenvectors are important. So with that, thank you for joining me. Take a look at the practice problems corresponding to eigenvalues and eigenvectors, and I'll see you in the next video.